Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this example, we have two different areas here that are sitting in a uniform magnetic field pointing horizontally. And we know that the first area here is tilted up an angle phi from the horizontal, where phi is equal to 12 degrees. And the first thing we're going to do is, given that we know the strength of our magnetic field and that angle there, we're going to figure out what the area of our loop is. So the strength of this magnetic field is just 0.47 teslas. Okay, so just for this first configuration here, we know that if we're tilted up from the horizontal by a degree phi there, then our surface normal is going to be pointing like this, where the angle it makes with the vertical now here is the same as that phi there. So this angle is the same as this one. So if we drew our the angle between the magnetic field and the vector that is perpendicular to our surface there, it would look something like this. So here's B, and then our surface normal would point a little off like that. So we now know that this angle is 12 degrees. So this angle here on the other side must be 90 degrees minus 12 degrees, because originally they were perpendicular to each other. So 90 minus 12 degrees is actually the angle that the surface normal makes with the magnetic field, not 12 degrees, which is up here. So when we plug into our equation for the flux, which is just going to be the flux is equal to the strength of the magnetic field times the area of our loop times the cosine of the angle between our surface and the magnetic field, we're going to plug in 90 minus 12, or 78 degrees, instead of 12 degrees. All right, so now, since we know what the strength of the magnetic field is, what angle we need to plug in, and what the magnetic flux is, which I just think I neglected to write down. Yeah, we know the magnetic flux for both loops is just 8.4 times 10 to the minus 3 Webers. So since we have everything but A, we can just solve for A. So if we divide both sides of our equation here by B cosine theta, we'll cancel it on the right side, bring it over to the left side, and we'll just have A is equal to capital phi over B cosine of theta, where theta is 78 degrees. Okay, so if we plug in all of our known values there, we will get that the area, specifically of the first loop, is going to be 0.086 meters squared. Okay, so now for the second part, here's the question. Given that we don't know anything about the orientation of our second loop, we just know it's in a similar situation as number one, but we don't know what the area of the loop is, and we don't know what the angle is. We just know it's sitting in the same field. So given that we don't really know what the angle is or what the area is, what is the maximum that our area can be, given that we know the flux for both loops is 8.4 times 10 to the minus 3 Webers. So again, we're just going to refer to our equation for the flux. So the flux is equal to B times A times the cosine of theta. And again, we're just solving for area. But this time we'll have, area 2 and angle 2, because we're talking about the second configuration. So I guess we should put in a theta 1 in our original equation, just to be consistent. But if we solve it the exact same way, we'll have that the second area is equal to phi over b cosine of theta 2. And now we have to ask ourselves, well, how can we make this area as large as possible, or as small as possible? And the way we can make the area as small as possible, well, we can think about it a couple ways. The first way is mathematically. I can think, well, if I want to make A small, I want our cosine of theta here to be as large as possible, right? Because dividing by a bigger number will make this smaller. And the biggest cosine of theta can be is 1. And if cosine of theta is 1, then we know that the angle, so cosine of theta 2 is 1. This means that theta 2 is 0, right? So that'd be the sort of mathematical way to think about it. Now, if we just refer back to our drawing, we know that we can maximize our flux whenever the field is completely perpendicular to the surface normal, or sorry, completely parallel to the surface normal. So in that case, our loop would be completely vertical, like this, so that the field passes through it like that. And again, if that's the case, the angle between our surface normal and the magnetic field is just going to be 0, because they're pointing in the same direction, right? So like this could be our surface normal here. And the black ones would be our magnetic field lines. But either way, we're going to end up with the fact that theta sub 2 is 0, and the cosine of theta sub 2 is 1. So the smallest area would have to be just the flux over B. So I'll put A2 small is just the flux over B. And of course, we have both of these values. And if we plug them in, we'll get that the smallest value for the area we can have is 0.018 meters squared.